Hi everyone. So today I will show you and share with you two exploits I've developed for Pwn2Own, two vulnerabilities in Windows kernel drivers. And in the way we'll see about the Windows kernel security, the mitigation, and the exploitation technique. So first, I would like to speak a bit about me and the company I'm working for, because it's thanks to them that I could participate to Pwn2Own and I could come here to present this to you. So I'm Thomas Imbert, and I'm a security engineer at Synactive, which is a French offensive security company doing pen testing, reverse engineering, development, and incident response recently. We have office in France, and if you're interested, we are hiring. Feel free to talk to me after. So today, what we are going to talk about. So first, I will introduce what is Pwn2Own. It's a competition, and we will see what it's about. Then I will speak about the first exploit, which is a use after free in cloud filter driver. And we will see how did I found the bug and how I exploited the bug for Pwn2Own. We'll quickly talk about the Windows kernel mitigation because there have been some recent advances and those could break the exploits, so it's interesting to see what is happening in Windows kernel. And after that, I will show you the second exploit, which is a more powerful vulnerability, and I will show what the vulnerability is and how I exploited it for Pwn2Own. So first, what is Pwn2Own? So Pwn2Own is ethical hacking contest. It's organized every year by ZDI, which is Zero Day Initiative, a company by Trend Micro. And it's ethical because the vendor are present and are given the exploit and the vulnerability. And there are multiple editions, one for IoT, one for desktop application, and I think there will be one for automobile application too. So I participated with my company to the Pwn2Own edition in Vancouver this year, in March, and I presented two Windows exploits, and the edition was not only about doing LP, so local privilege escalation on OS. You could target application, virtualization software, browser, OS, and even a car. The Tesla was a target. So how does it work? The competition is announced a couple of months before it happens. So you are given a couple of months to work on exploits. And the exploit has to be 0 day because on the competition it will be run on latest updated software. You have one entry per target usually, and I presented two Windows LP, but the first one was a standalone, and the second one was actually a chain. So my colleague at Synactive wanted to target a VirtualBox. So to do an escape from the guest to the host. And after that, we chain Windows LPE to get administrator privilege on the host. And so we had two entry, one standalone and one part of the chain. And then when you arrive at the competition, the order is random, so you don't know, so you are assigned a slot. And you have 3 attempts or 10 minutes to showcase your exploit, and if it's successful and not a duplicate, you get the prize. So this is a quite long 10 minutes to trigger vulnerabilities. This allows you to have something that is not 100% working or something that could be long. It's really interesting. And actually the Pwn2Own went well for us because we won almost $500,000, more than $500,000. So this is not all for me, but hopefully next year. So my company. So we presented entries on Windows, macOS, and Ubuntu LPE. We presented the VirtualBox escape and some Tesla LCE and LPE to get that amount of money. So it was actually a lot of work. So now that you know more about the competition, let's go into the first exploit. The first exploit is in a cloud filter driver. But first, I want to tell you why did I pick this driver. So Pwn2Own actually require you to exploit a vulnerability in kernel mode. You cannot focus on user mode services. You have to pick something in kernel. It's the rule. I don't know why, but it's like this. And as I told you before, we have a long 10 minutes for each attempt at the exploit, so we can target on something that is not really reliable and that takes a lot of time. So you could use bugs that are not really powerful. So the idea, my idea for this year was to try to find some interface that was not using classic IOCTL, in the hope that it will be less review, less fuzz by Microsoft and by other. So I wanted to pick something different and hope for a quick find in a driver using this. So I picked the filter communication port, which is a technology to communicate between user and kernel mode, used by mini filter driver. And the driver registers a port by name, and then the user mode application can connect to that port using a API which is filter connect communication port. The port is named, and then it will be able to send message, receive message, and reply to kernel mode message. And at that time I didn't know, but this is actually implemented using IOCTL, so it's the same interface that I didn't want to review. But this is abstracted by the filter manager. So the one driver is actually handling the request and sending to the target filter driver all the requests we send. And so this is not exactly like reviewing IOCTL only. And so I reviewed the list of drivers using filter communication port to find a target. And there is actually only one that is really interesting and reachable from unprivileged user. It's the cloud filter port. And it's interesting because it has it's pretty complex. It has like 20 different messages. It does asynchronous message also, so there is a good chance that there will be race condition. And so I decided to pick this one, pick the cloud filter driver, and just take a couple of days to look at it and see if I could find some bugs. Found quickly some race condition, but it was something really hard to trigger, so I decided to go for another approach, and because of the complexity and the limited time I had for Pwn2Own, so I decided to go for fuzzing, and we will see that after this slide. So first, what is the cloud filter driver? So this is the kernel mode driver responsible for OneDrive, so for cloud file system. The API is actually documented. It's the cloud file API. And how does it work? So you have this kernel mode driver. It's actually a file system mini filter. And file system mini filter can modify the behavior of the file system. They receive callback when you open a file, when you read a file, when you write to a file, they receive callbacks, and they can do whatever they want. And the driver is only responsible for forwarding those callbacks to a user mode process, which is called the sync provider. And this user mode process will sync with the cloud. So for OneDrive, it will sync with Microsoft Cloud, but you can implement what you want. You can have your own sync provider. And this sync provider will claim a directory. And said this directory is actually in the cloud, and then you can place placeholder in this directory, which are basically empty file. And when someone wants to read one, the kernel mode driver will be called. It will call the sync provider, and the sync provider will be able to talk with Azure or any cloud provider to get the file content and hydrate. This is called hydrating the file. So this driver is basically just creating placeholder for you, creating fake files, and giving you callbacks on access. To simplify. So I decided to understand the driver by writing a sample harness. So using the API that were documented in the Cloud Filter documentation, in the Cloud Mirror sample, to just interact with the driver and see how does it work and what could happen if you send bad message. This driver also is interesting because James Forshaw from Project Zero, he found some logical issue in this driver. So not memory corruption, but things with file ACL that were wrong. And so it's interesting because if there are some bugs, there are probably more. And he didn't look for memory corruption. So I keep implementing the harness. So basically I created a few placeholder file and I implemented the callbacks. So as you can see on the right, you got the kernel mode function that are getting notification when something is open, read, or write. And this kernel mode callback will send a message using the filter API to the user mode sync provider, which is our process. And in the callback, we can fetch data, acknowledge file deletion, file rename. So we got control on what happened in this cloud file system. And so I implemented this, not all the callbacks, but some of them, and I implemented those with error and mutation. The goal was just to have some sync provider that was doing random operation, and the goal was to exercise most of the code in the driver, because we want to fuzz it, so we want something that reach most of the code. So I implemented this. But the sync provider alone won't work, because it will create a cloud directory, but if nobody interacts with the file, nothing will happen. There will be no callback. So I wrote a sample client to do open, read file, delete, just to exercise the driver and the user mode process. And now we can start the fuzzing, but before that, just you have to configure the crash dump, because you will be getting some crashes. And also one thing I try to do every time I fuzz kernel driver is to configure special pool, which is a verifier option. And so special pool is actually a different heap in the kernel. And when you specify the driver name, all the allocation made in those driver will be placed into that special heap. And this heap is interesting because it catch memory corruption. So when you have out of bound access, you have better chance to catch it with special pool, because the allocation will be placed at the end of the page and the next page won't be available. So the kernel will just out of bound and crash instead of corrupting something else. And when an allocation is free, the page is also released. So if you have a user stuff free, it will be caught because the access will crash instead of reading or writing garbage data. So it's always a good thing. And after getting a few null references that are not interesting, I got a crash after a minute, who looked way more interesting because we got write access on some garbage data that is supposed to be a pointer, and as we can see, it looks like a white string. So this is probably something we can control. And actually, there is also something else interesting. It happened in Explorer. So this is not in the sync provider or in the client process. This is in a different process that actually called an API I was not using, the query process. And this bug, this crash is interesting because we can see that we can probably control that pointer, and there's a write access, and the pointer is supposed to be a IRP object, and we will see what we could do with that crash in IO cancel IRP later. So when I got that crash, it took me 2 or 3 days to understand the crash because I didn't have much context, and the fuzzer was just generating random stuff. I didn't spend time to minify the POC. I tried to understand the root cause before continuing. And this is actually use after free, and we don't see a crash right away because the use after free, between the free and the use after free, there is a minute delay. And this minute delay caused the allocation to be reused by something else instead of being just a page that is not present. And so the crash is not, is a bit more complex. So to understand the bug, we need to get into the internal of the cloud filter driver. So in the kernel, when there is a file operation, there is a IO request packet that is associated with it. So when you do file open, file read, or IOCTL, it creates a IO request packet, the IRP. And this IRP, it's stored inside the IRP control object inside the filter manager. So the filter manager has a structure that saves the IRP and saves the metadata about the access and the callback data for each file system operation. And the cloud filter, so the vulnerable driver, it stores the address of the callback data for every pending IO access. So when something is not responding directly, they will store that access, that callback data on a list, a global list. And after a minute, if the request is still ongoing, the IRP will be cancelled. And so this is a way for the cloud filter to prevent file access to be to DOS the computer, because after a minute the file access will be cancelled. So if you are trying to open a file that in a cloud file system and you don't have internet access or something, the access will not freeze. It will freeze only for 60 seconds, and after that it will be unlocked. And so they implemented this list and this minute just to catch files that are sync provider that are not responding. And the bug is that after a minute, if you kill the sync provider, the object is free, so the IRP control object on the bottom right is free, but the list still point to it. So you got the double chain linked list with two objects. So one started 1 minute ago, and one started 3 seconds ago. And the first one, the sync provider, was killed, and so the IRP control object was free. And after a minute, after the cooldown timer is happen, the IRP pointer will be dereferenced from that use after free object. And so this is the bug we we have seen in the crash the cancel IRP, because the IRP was in an object that was freed, and so it was containing garbage data. And actually, to trigger this bug is a bit complex. And the fuzzer found it because I was killing the fuzzer after a minute. But to implement this, it took a bit of time. So we need 3 different processes. One sync provider that is never answering the file deletion. I'm doing that with file deletion, but I could do that with file read or file write. You just have to not acknowledge the file operation. And then we need a client process to actually delete that file, and another process that will kill both of them at specific timing. After that, the IRP control object is free, and you need to wait a minute and call the query process API to trigger the use after free. Okay, so it's a bit complex bug, and it takes you have to get the timing right to make it work. But what does this give us? So we have a field which is the IRP pointer that is read from use after free object. So if we can spray data to reuse that allocation, we can control that IRP pointer, and it's passed to IO cancel IRP, and there is no effect after that. So we can just analyze the IO cancel IRP function. And as you can see, there's a lock taken, then there's a write of the value 1, and then there's a function pointer call. And so we have 2 ways to exploit that. Either we could use the write with the value 1 or the function pointer call. If we control the IRP pointer, we can make it point to anywhere. And so I actually, for Windows kernel exploit, mostly do the same thing every time. So the goal is to elevate your privilege to system and then run a beautiful shell. And the technique I use, there are multiple techniques, but the technique I use the most is to corrupt the current process token privilege. So a process has different privilege, and by default it doesn't have a lot, but administrator process can debug, can create a global object, and can do a lot of things, can backup. And so if you manage to corrupt your own privileges, you could debug any process in the system. So that's a good technique. And the only thing that it requires, it's an arbitrary write and information leak of the token object, because you need to be able to write the bit field, and you need to know where to write to get that shell. A good thing for us is that we are running as medium integrity for Pwn2Own context. We are not in a sandbox, so we can just ask the kernel API for the kernel mode address of the token. So this is a bit weird, but Windows work like this. You have a very old API that gives you the address of kernel object. We can also get the address of a system module using a different information class. This doesn't work in sandbox, but for our case, it works. And then there are more mitigation we need to take into account. So the function pointer, if we corrupt it, there is a SMAP and NX. So we need to make sure it points to kernel memory executable. We are lucky because on Windows, map is not enabled. It's not enabled in most situations. There is some interrupt that set it, but it's not enabled. So that means that we can have a kernel, something executing in kernel, reading and writing to user mode memory. So we can fake object in user mode memory, and it will work. It won't crash. And for the reuse, so we need to spray something to reuse the use after free allocation. And this is documented on the internet. We can use namepipe data entry with the same size, and it will work most of the time. And there's one mitigation that is more important in our case. It's a Windows kernel control flow guard. So when I said previously that we control the function pointer is not called directly. There is a call to guard dispatch icall, and the function pointer is checked to belong to a list of valid target. And if it's not a valid target, it will blue screen. So we can only call valid function. So we cannot call rob gadget. We cannot jump on inside of a function. We have to call the function entry. So let's do something with that. So we can control the function pointer and the address of the two parameters. So we can let's just chain multiple functions that we have the right to call to get arbitrary right. So to do that, I found a chain of function. So the first one is the cancel routine. This is important because in IO cancel IRP, there is a lock taken, and if we don't release that lock, it will crash. So this function is actually releasing that lock and then calling something we can control, because we control the IRP address. So we can control the address of the function being called and the first argument. And so we forge everything in user mode to get the function pointer and the argument. Then we call another function to get the control of more parameter. So we have only the control of the look aside address, and with that function we can jump to another function and we can control 3 different parameters. And the last function we call is a RTL copy Unicode string to get our arbitrary right, because we control the 2 parameter address. We can forge the address of the buffer and either get arbitrary read or arbitrary write using this mem move. But we want arbitrary write, so we write. We specify the address of the buffer is the kernel token. The source is somewhere in user mode, and the size is the size of the privileges. And then we get arbitrary right. Okay, so yeah, this was a lot of things, but basically we got a way to reuse the allocation, so we can control the IRP pointer. We got a chain of function to bypass the CFG mitigation, so we can get arbitrary write. And we know where to write because the token can be licked, the token address can be licked using the anti-query API. So we got everything we need. We can just write the full chain, the full exploit, which takes a bit of time. So we forge every fake object in user mode. We trigger the vulnerability. We spray data to reuse the allocation. And then we wait a minute, because we have to wait. The vulnerability only works after the timer of a minute is exhausted. We trigger the use after free. And at this point, if everything happened correctly, the arbitrary write should have corrupted the token, and we should have a process with all the privileges. And we can just spawn a shell using the debug privilege to spawn a shell as by hijacking win-logon process. Okay, so we have an exploit working. I won't demonstrate it here because it takes between 1 and 6 minutes because of mostly one problem is that when I said previously that the RP control was freed, it's not right. There is for performance, there is a look aside list. So when the allocation that is supposed to be used after free is only freed if the list is full. So we need to play this vulnerability multiple times so that the use after free chunk is actually free. And so it doesn't work all the time. When you just booted the computer, it worked most of the time, but after some time, the list grows in size. And so if the list is big, it's you need to play the vulnerability a lot of time to fill the list, and reduce the chance to work. But this is okay for Pwn2Own because even if it takes a lot of time, a minute for an exploit is pretty long, and even if it doesn't work all the time, we have 3 attempts of 10 minutes. And so the first attempt, I was behind the screen for 6 minutes, just looking at the screen, doing nothing. And after 6 minutes, we got a crash. So yeah, bad luck. And the second try, it worked. So the exploit worked and the vulnerability was not none. So this is the first bug for Pwn2Own. So just for some statistic, the exploit actually took almost a week to do everything, between the manual review, the fuzzing, the root cause, and the exploit itself. And I won and it worked for Pwn2Own. Before talking about the second bug, the powerful bug, I want just to give you feedback on Windows kernel mitigation, because I asked myself the question, will it work next year? And so we know that Microsoft is actually working on mitigation to kill bug classes. They killed most initialized memory vulnerability in the kernel by zeroing the heap and by zeroing the variable. They are trying to catch C++ type confusion vulnerability. I think it's only in user mode right now, with CastGuard. So they are investing a lot to kill bug class, but also they are investing some time to kill exploit primitive. So the thread previous mode overwrite doesn't work. It was a technique to get arbitrary read and write just by writing a 0 in the previous mode field, and the thread will be considered kernel, and you will have all the write on kernel memory. And recently I learned that they are trying to kill the KSLR by design info leak. So this is the thing we use to leak the address of the token and to leak the address of module. This is going away, apparently, thanks to the security community tracking change on insider build. Microsoft is currently implementing a mitigation to remove the function pointer, the kernel pointer inside the anti-queries API. And if we don't have that, the bug will require an info leak, because you will need to jump on a kernel function, but you don't know the address of kernel module, so you will need a leak. Also, there are more mitigation that could break the exploit, but are not enabled on Windows or are not powerful enough, like SMAP, to block access to user mode memory in the kernel. This is not enabled on most of the code, because the kernel can access user mode memory at any time. It could read the peb, read the tab, or read the user parameters, and so this is not enabled. And actually, in our case, the use after free happen when we are running as a IRQL that is not supposed to access user mode memory. So it could be enabled, and this could prevent us from forging object in user mode memory, but it's not enabled, so it's good for us. And also the CFG implementation is really limited in the kernel because they allow a lot of targets, and this could be improved also. I don't know if Microsoft is working on this. I know they have a stronger solution for user mode, but in user mode they control most of the code running in the process, so they can have something that doesn't have any third-party code, and so they can compile harder mitigation. And both SMAP and CFG in the kernel will be hard to improve because of third-party driver and a lot of work to actually improve those mitigation. There are also two mitigation I want spend a lot of time on this because this doesn't impact the exploit. There's a CET, the hardware mitigation in the CPU to use shadow stack and control transfer instruction to protect the control flow hijacking. But this won't work in our case because it doesn't prevent to call function. It only prevents to corrupt the return address or to jump to inside the function. And HVCI is also not a mitigation that is designed to prevent us from getting LP because it's only trying to protect kernel mode code, and we are not executing custom code, we are executing the code of the kernel. So to go back to the question, will it work next year? Actually, Microsoft is doing a lot on high impact scenario, so reducing attack surface, hardening sandboxes, but for the local privilege escalation from unprivileged user, I don't think this is a priority. So they are doing some stuff, but I don't think it's enough to really improve the security and make it impossible to exploit. So next year, it won't probably work because of the KSLR mitigation. But I still think that with one kernel bug, you could exploit the Windows kernel. You just need maybe a better bug to leak something and to write some things. Speaking of more powerful bugs, I decided to do a second exploit because my colleague was targeting VirtualBox, and he told me we could have an add-on, and so we could chain a VirtualBox exploit with another vulnerability, with the LP on Windows side, and I didn't want to use the first one because it was not really reliable, and I didn't want to, if some vulnerability in the chain failed, the full chain fails. So I wanted to have a stronger bug that worked most of the time. So I got a bit lucky. I decided to review and to find a quick win in some driver. And I picked driver in the file system, looked for sample issue in just the few function handling the IOCTL, and if I don't find anything in 10 minutes, I just skip and pick another driver. I found a couple of bugs in driver like this, but it was either in optional feature or impossible to load. So you don't have admin access with unprivileged user, so you cannot load any driver. And so by looking for driver in the file system, they won't be always loaded. But I got lucky. I found MSKS SRV, which is part of the Microsoft streaming service component. It's not loaded by default, but lucky for us, when you open the path to the driver, when you ask for an handle to the driver, the plug and play component will load it for you. So there is no need to admin privileges. The driver is not loaded, but on demand it will be loaded for us, even if we don't have the right to load drivers. And what is this driver doing? It's allowing two processes to share memory, and this is abstracted in the driver. We use the term transmit and receive stream, but basically you can share memory between two processes, even if the two processes don't have the same privilege, don't run as the same user. You can use that driver to do everything for you, to map the memory, and that's it. So I got lucky. I found this lines of code, and immediately I thought something was wrong. So it's hard to see. So yeah, that's why to get lucky, you probably need a bit of experience and be used to the Windows API or the system you are targeting. So the code that is wrong is the mmprob and log pages. So the mmprob and log pages is called with the MDL and the value 0, which is the access mode, which is supposed to say if the parameters are coming from kernel mode or user mode. and the parameter here are coming from user mode, but the field is set to 0. So this is saying this is kernel mode parameter. And on Windows, on every OS, the kernel must validate the pointer of that are coming from user mode. And on Windows, this is called probing. They use prob function like prob for read and prob for write. And this validates that the object you are passing to the kernel is indeed in user mode. Otherwise, you could pass a kernel mode pointer and read from that, write from that, and there will be no boundaries between the user and the kernel. So this API, this probing is important for the security of the kernel. And as you can see in the code, if you actually pass the user mode access mode, there will be a check to see if the address is not belonging to the kernel. And here we don't have this check, so that means that this IOCTL 2F0408 is accepting kernel mode pointer, and that's pretty bad. But at this point we don't know how it's used. It's used in MDL creation. What is a memory descriptor list? It's actually a kernel mode object that refer to that save virtual memory range. So this object is a kernel object, so you cannot control it from user mode. It's only in kernel. And this is used for I/O operation or DMA to map and lock memory. So if you are trying to pass a large buffer to the kernel, there is a good chance that the kernel will create a MDL to lock the memory and then read from it or directly map it to kernel mode memory. So this is used a lot in the kernel, and this is just a way to specify virtual memory ranges and to map it and to lock it. The MDL also store the physical address of the virtual memory range inside the object. So this MDL is actually used to in the driver to map it to another process. As I told you before, this driver is used to share memory between two processes, but the memory is not checked to be within user mode boundaries. So we have one API that creates a MDL from a kernel mode pointer or user mode, but we will use a kernel mode. And this kernel mode pointer could be mapped to user mode. So the same physical page will be mapped to user mode virtual address. And what does this give us? We can map arbitrary kernel memory to user mode and control it. So we get arbitrary kernel read and write using just the bug. So it is really powerful bug. It's really interesting. But there's still one thing we need is we need to know we need to know the address of something in kernel to map it. Because if we specify a wrong address, it will crash. It won't be able to find the physical pages and it will crash. So we got arbitrary kernel read and write, but we don't know where to read or where to write. But fortunately we have the token. The same technique for the first exploit is working again. We can leverage the KSLR infoleak to get the token address. Then we can map the token to user mode, corrupt it, and then we get all the privileges, including answer debug, and we can open the shell. So this is after everything is written. This is only 4 lines of code. We just map the token to user mode, corrupt it, and then start the shell. So this is a really nice bug. The missing prob are usually very nice bugs because it gives you either arbitrary read or arbitrary write in kernel. This is nice because we get both read and write, and we can control the values we write. And so this is 100% stable. There is no mistake we can do. This is really fast, and actually, it didn't take me a lot of time to write the exploit. I just copy pasted the method from the first exploit, and just added the vulnerability and it worked. So I think it took me like 3 hours to write the exploit, to find from the bug finding to the exploit. And this worked at Pwn2Own also. The second time, why? Because the first time, the VirtualBox exploit dropped the LP binary on the host and tried to execute it, but the antivirus, when Microsoft Defender, thought that this was a virus, and so it removed the LP payload, and nothing happened because Microsoft Defender blocked the LP payload because it was not obfuscated, or it was not. It was spawning a command, which is probably something they have detection on. And so the goal of Pwn2Own is not to bypass the antivirus, so we just disable the antivirus and run the full chain again, and we managed to escape VirtualBox and get admin on the host. I will try to do just a demo. I don't know if I can. Okay. Can you see that? So this is running as unprivileged, so we cannot directly go to. We don't have access to user files, but if we run the exploit, okay, oh yeah, the window pop on the other screen. So we get the system shell. Yeah, the window pop on the other screen, but but trust me, it's working. And so basically what we do, we get the token address, we map it to user mode, and then we corrupt it and run, and it's 100% stable. I can run it. I'm getting a lot of windows like this. Yeah. Oh, but yeah. Up. Okay. Nice. And so yeah, this is 100% stable and very fast. So it's a great bug to chain because we wanted something really reliable. We didn't want to fail the chain. And so to conclude, I think Pwn2Own is really a great opportunity to challenge yourself and to learn, because you have a time limited. You have time limited to find a bug and exploit it. You don't have to write the perfect exploit. If it works half of the time, it's okay. You will be a bit stressed, but it's still a good opportunity. And Windows is a good target because you are not starting from a sandbox. You are starting from unprivileged user, so you get a lot of attack surface. You got the KSL info leak to help you. There is a lot of documentation available online. So it's really it's a good target. So both bugs I presented are patches. They were fixed in June, so 3 months ago. I think Microsoft took from March to June to patch it, so it was quite fast. And yeah, I recommend to try Pwn2Own. And to give a few words about the Windows security, I think it's slowly evolving in the kernel, but right now it's still possible to attack with limited means. It's not like other OS where you need a team of reverse engineer person to find a bug and exploit multiple bugs just to get LP. Here with one person and sometime you can get LP. And so it was a great experience for me and to learn, and I'm happy to have participated to Pwn2Own and to present this to you. I would like to thank again my company, and thank you for attending.
Are there any questions? Okay. Oh, yeah.
You mentioned on the second bug, and you have to pass a kernel pointer to just mapped and to gain the kernel read and write. So how do you know the exact value of the kernel pointer?
Okay, so yeah, so this is used the KSLR info leak. I think I have some slide to present it. Yeah, this is using the anti-query system information with the system extended handle information. So basically, you ask for an handle on your token. So I don't remember the exact API name, but you open your own token, open process token, it's called, and then you call this API. And because you are not in the sandbox, it will return all the handle used in the system with the value of the handle and the value of the kernel mode pointer associated with it. So you can get the kernel mode just by calling this API and finding your handle in the list. So this is by design on Windows.
Okay. Will you disclose this POC for the second bug?
I don't know. I need to ask my company. I haven't asked, so I think myself I'm okay, but I need to ask my company and ZDI to know if I have the right to write the bug, because there are more than actually two. Here I said there are only two IOCTL, but you need to initialize the driver. You need to register two streams. So actually it's 5 IOCTL you send. So it's not a tweetable POC. it's like a 50 line. But yeah, I will ask my company if I can disclose it.
Okay, thank you.
Any other questions? Okay. Thank you very much again.
Thank you.
Round of applause.